All right, welcome to Unit 4 and Lesson 4-1A. Now, as we head into Unit 4, we're actually sort of turning a major corner here in calculus. We spent the entire first half of this course basically really talking about limits and derivatives in particular, and derivatives being a rate of change. As we start Unit 4 from here and beyond, we're actually now looking at a second aspect of calculus. So derivatives was one of those major aspects. Now we're starting to build the foundation to look at the second major aspect. So for today, we're going to talk about finding area under the curve. That's the phrase you're going to hear me say quite a bit, area under the curve. So in front of you, you see this graph, and this is just some random function f of x. And the question is, how can we approximate the area of the region that's bounded by f of x, so the curve, x equals a, so this vertical line here that starts at x equals a, x equals b, this vertical line here on the right, and the x-axis. So in other words, this green shaded region. How can we approximate the area of that? And first of all, the reason I even say approximate is, you know that for a geometric shape, say a rectangle or a triangle or a circle, we have formulas for those. We can find the exact area of those using geometric formulas. But this region that you see in front of us, this is not a regular type of a geometric shape. There is no formula we can just plug into to find the area of this. So the question is, what can we do that would at least give us an approximation for that area? And so a good deal of calculus is actually going to focus on that question. And a little bit later in today's lesson, I'll talk about why that's an important thing. But I think that discussion will make a little bit more sense after you've seen how we can approximate this. Okay, so again, the question is, how can I approximate the area of this region since it isn't a normal geometric shape? Well, there are actually a few different ways, but most of them involve cutting up this region into smaller shapes that are familiar geometric shapes. And again, remember that this is an approximation, so we already know that the area that we're going to find by doing this, it's not going to quite be correct. It's going to maybe be a little too high of an approximation, might be a little too low. All right, so again, there are actually going to be 4 different methods for approximating this area. 3 of them are going to involve rectangles. One of them is going to involve trapezoids. So let's take a look at those. So the first of these 4 approximation methods is going to be used using what's called a left-hand sum. So like I said, we are going to try to divide this region into smaller known shapes. So with a left-hand sum, we're going to use rectangles whose heights are determined by the left endpoint of the base. So let me show you what I mean by that. So if I take, for example, starting at A, and maybe I'm going to make the base of my first rectangle from A to this value right here. So that's now the base of my first rectangle. Now, the height of that rectangle for a left-hand sum will be based on the function value at the left endpoint of the rectangle. So here's the base, here's the left endpoint, and if I go up, there is going to be the height of my first rectangle. And so as you can see, that rectangle actually extends a little bit above the curve for most of that section. So clearly when I use this rectangle, that's going to end up giving me a little bit more area than we actually have. Okay, but now continuing from where I left off, so from this right endpoint of that first rectangle, that's now going to be the left endpoint of my next rectangle. So maybe now I'm going to have another rectangle that goes to here. So this is now the base of my second rectangle, but again, the height will be determined by the function value at its left endpoint, so that's going to be right here. And so now if I draw the rest of that rectangle, it looks like this. And so in this case, you can see that this rectangle is actually a little bit too short, and it's missing some of the area. All right, and I can just continue on. So in this particular instance, I happen to just divide this up into, it looks like about 5 rectangles. one more. All right. So those 5 rectangles that I just sketched, if I were to find the area of those 5 rectangles and add those areas together, that would give me an approximation for the area under the curve, that green shaded region. Now clearly, I'm missing a whole bunch of areas, and then I have a little bit extra here. So again, this approximation is clearly either going to be too much or too little, but at least it's giving us a ballpark estimate. All right, now remember, to find the area of a rectangle, it's just going to be base times height. So for each of these rectangles, we just have to measure what is the width of the base. And then for the height, remember we're using the function value at whatever the left endpoint of the base is, which would be some value of x. Okay, so that's a left-hand sum. Okay, so if we had a left-hand sum, then that also means that we can have what's called a right-hand sum. So hopefully it makes sense then that the right-hand sum, the idea is now we're going to use rectangles again, but this time the heights of those rectangles will be determined by the function value at the right endpoint of each base. So again, if I were to choose that first rectangle to go from A to, let's just say this value right here, well, now the height of that rectangle is going to be the function value on the right endpoint. And so now I would draw the rest of the rectangle there. Okay, so in this case you can see that this rectangle was just a little bit too short, so it's missing some of that area. But now for my second rectangle, again, if I go from where I left off to here, so again, now my height is right here. And now you'll notice that that rectangle actually extends a little bit above the curve. So now I'm including a little bit too much area. And again, if I were just to continue with, let's just say 3 more rectangles. And again, each time, the height is determined by the right endpoint function value. Oops. Again here. And finally this last one. Whoops. Very messy. All right. So this time, as you can see, for this particular function, again, this is not all the time, but for this particular function, many of these rectangles actually ended up extending above the curve, definitely giving me too much area in those cases, and then this first rectangle missed a little bit of area. So again, this approximation is clearly not going to be precise, but it is going to give us a general idea. All right, so again, that's a right-hand sum. Once again, we were using rectangles where the height of each rectangle was determined by the function value on the right endpoint of the base. Okay, so for the midpoint sum, this time, as the name implies, we're going to use rectangles whose heights are determined by the function value at the midpoint of each rectangle's base. So once again, if I were to start at A, and maybe the first rectangle ends right here, so there's the entire base. But now the height of that rectangle is actually going to be determined by the function value at the midpoint of that base, which would be right up to here. So that first rectangle would be right about there. And then again, if I were to do another rectangle right next to that, but again, I'm going to have to now determine the height from the midpoint. That's going to be right about there. And again, let's just, in this case, let's just do 2 more. And we've got this midpoint right there. All right, so that's the idea of a midpoint sum. And you can kind of hopefully see the advantage maybe of using this midpoint sum. Notice each rectangle for this particular curve, part of that rectangle extended above the curve, but part of it was still below the curve, meaning any extra that we have was partly balanced out by any area that we missed. So you might assume that maybe a midpoint sum is actually going to be a fairly more accurate one. Again, still not precise, but as an approximation goes, it's probably going to be a little bit more accurate than a left or a right-hand sum was, at least in general. But again, all of this depends on what the curve actually looks like. Okay, so those are the three different types of approximation methods that use rectangles. Now let's talk about the fourth one, which uses trapezoids. But before I can talk about trapezoidal sums, I think I probably have to refresh your memory with trapezoids, because I have a feeling that that's something that you probably haven't had very much practice with, or any practice at all. So, as a reminder, or maybe for the first time, a trapezoid is a quadrilateral, so it has four sides, where exactly two sides are parallel. Or in other words, it has one pair of parallel sides. Okay, and those parallel sides are both called the bases. So this is a base, so maybe base 1, and then this other parallel side is the other base, so maybe we can call that base 2. And then you also still have the height, which is the distance, the perpendicular distance, between those two bases. So that right there is the height. Okay, so again, a trapezoid is any quadrilateral, so any four-sided figure, that has exactly one pair of parallel sides. Now, for our purposes, the specific type of trapezoid that we want to look at are the kind where the height is actually one of the sides of that trapezoid. So in other words, notice how in this trapezoid, the left side is actually the height. And then my two bases are there. And then what we're actually going to do is we're going to actually rotate this trapezoid 90 degrees so that the height, the flat side, is actually on the bottom. So notice this is now the height, and then this is now the height. And then those parallel sides, the bases, are actually running vertical. So that's actually the type of trapezoid we're going to be looking for. Okay, now for trapezoids, the area, I'm guessing you aren't familiar with this one, the area formula is 1/2 times the height times the sum of the two bases. This is the formula for the area of a trapezoid. You actually do need to memorize that. Okay, so if you didn't already know that formula, and I'm guessing that's many of you, you do need to learn and memorize that formula. The good news is you will most likely memorize it very quickly from doing this lesson. Okay, so this is how you find the area of a single trapezoid. So here's the idea for a trapezoidal sum. We're going to use trapezoids that are rotated, whose heights measure along the x-axis, and whose bases are determined by the function value. So it's exactly like what I was showing you. So for this first trapezoid, again, we're going to start at A, and let's just go to, well, let's say right about here. So this distance in the x-axis right there, that's actually going to be the height of the first trapezoid. And then the bases are going to be determined by both endpoints, the function value at both endpoints. So there and there. And then the fourth side just connects those. So that's actually the first trapezoid that we're looking at. And then again, I can go from where I left off to another point. So again, that's actually the height. And then the two bases get connected by that fourth side. Again, I can do another trapezoid. For time reasons, let's just do 4, and I'm going to pause and make it magically appear. All right, and so with the other trapezoids drawn in, that's what our area or our region would look like. So as you can see, this is actually pretty nice because that angled side of the trapezoid, the side that connects the two vertical bases, it almost traces along the curve of that graph. So again, you can probably assume that a trapezoidal sum is probably going to be a fairly good approximation depending on the function and depending just how wide we made each of these trapezoids. Okay, so these are the 4 different approximation methods. We had a left-hand sum, a right-hand sum, a midpoint sum, and a trapezoidal sum. So let's take a look at an example how we do that. Okay, so the table gives selected values for a function f of x. Approximate the area under the curve on the interval from 2 to 12 using the indicated method. So we're going to start off with a left-hand sum. Now again, notice for this table they gave us selected values of x, or the function for selected values of x on the interval from 2 to 12. So remember, the idea is I'm trying to divide this region up into rectangles. And if I'm only given a table of values, I'm pretty much restricted or limited to the values they gave me in terms of how many rectangles I have, how wide those intervals are. So I have to go along with the data in the table. So for this first table, or for this table, the first rectangle is going to have to start at 2. Remember, that's like going from my A, and it's going to end at 4. So really, that's what my first rectangle is going to be. So again, it's starting at 2, and that first rectangle is going to have a width that stops at 4. And then remember, for a left-hand sum, the height is determined by the function value at the left endpoint. So in other words, f of 2. So for my left-hand sum, the area will be approximately, so for the first rectangle, remember a rectangle area is base times height. Well, the base is going to be the distance between the x's, so 4 minus 2. So that's the base. And then times the height. And remember, the height is going to be f of 2 because that's the left endpoint. For the second rectangle, now we're going from 4 to 6. So that base will be 6 minus 4. And then remember that the height is going to be determined by the left endpoint function value, so that's going to be f of 4. For the third rectangle, I'm going from 6 to 9, so that means my base is going to be 9 minus 6, and the height is going to be f of 6, because that's the left endpoint. And finally, for the last rectangle, we're going from 9 to 12, so 12 minus 9 will be the width, and then the height is going to be f of 9. And then now we just substitute in the values. So 4 minus 2 is going to be 2, f of 2 is 3.0, plus 6 minus 4 is going to be 2, f of 4 is 4.2, plus 9 minus 6, which is 3, f of 6, which is 7, and then 12 minus 9, which is 3, and then f of 9, which is 5.4. All right, and when you use your calculator, because yes, you would definitely be using a calculator for this, when you use your calculator to plug all of those in, you end up with 51.6 as your approximation. So again, we don't even necessarily know what this function looks like, but based on the information we were given, this would be the approximation for the area under this curve f of x on the interval from 2 to 12. All right, now for a right-hand sum. So for a right-hand sum, again, it's almost the exact same idea, except remember this time the height of each rectangle is determined by the function value at the right endpoint. But the width of the rectangle, the base, is still the same. So for our first rectangle, we're still going from 2 to 4. So again, that's going to be a distance of 2. And the height of that rectangle is determined by the function value at the right endpoint. So that's going to be 4.2. So in the first part A, you saw me really break it down into the actual mechanics. You saw me write 4 minus 2. You don't have to do that, but I did want to make sure that it was clear where that was coming from. So for the first rectangle, it's going to be a base of 2 and a height of 4.2. For the second rectangle, again, we're going from 4 to 6, so that means the base once again is 2, but this time the height is going to be f of 6, again the right endpoint, so that's going to be 7. Plus, for the third rectangle, we're going from 6 to 9, so that's a base of 3. And again, the height is going to be f of 9, which is 5.4. And finally, the last one, we're going from 9 to 12, and that's going to be a base of 3 and a height of 2.4. And when you use your calculator, you should get 45.8 for that approximation. Okay, so left-hand sum, right-hand sum so far. Now, what about a midpoint sum? Okay, now if you're taking notes along with me, hold off for just a moment. So for a midpoint sum, again, same idea. I want to find the base of the rectangle and then the height of the rectangle. Now if I try, again, don't write this yet. If I try to use the same base that I've done so far, that means I would be going from 2 to 4, so that would be a base of 2. And then the height would have to be, remember, the function value at the midpoint. Now, between 2 and 4, the midpoint would be at 3, but the problem is I don't know f of 3. They didn't give us that information. So I can't use a value that I don't have. But if you notice in the table, if I go from 2 to 6, the midpoint of that rectangle would be at 4, which I do have. So again, when you're doing a midpoint sum, you do have to check a little bit more carefully because you do have to make sure that the midpoint that you're planning to use for the height is in fact in your table. So now feel free to take notes or pick up your notes from here. So that means my first rectangle is actually going to go from 2 to 6, which is a base of 4. And then now the height is going to be the function value at the midpoint. So that's going to be f of 4, which is 4.2. Plus, now that means for my second rectangle, again, I can't just go from 6 to 9 because halfway between those would be 7.5, which I don't know the function value for. But I can go from 6 to 12 so that the midpoint occurs at 9. So if I go from 6 to 12, then that rectangle has a base of 6. The height is going to be f of 9, which is at 5.4. And so if I use my calculator, I get 49.2. So again, it's very important for you to keep in mind that you can only use the values in the table that were given to you. So if I'm trying to use a midpoint sum, I have to make sure that I'm choosing intervals that allow me to have information about the midpoint. Otherwise, I can't use a midpoint sum. All right, and let's wrap up here with a trapezoidal sum. Okay, so now for a trapezoidal sum, first of all, remember the area for a trapezoid is 1/2 times the height times the sum of the bases. But remember, for the trapezoids that we're using, the height is actually the width along the x-axis, and then your base 1 and base 2 are actually your vertical values, so your function values. Okay, so for our trapezoid, our first trapezoid, again, we're once again going to go from 2 to 4. So the height is actually going to be 2. Base 1 is the function value on the left endpoint, and then base 2 is the function value at the left endpoint. The right endpoint. So that means for the first trapezoid, the area will be 1/2 times the height. Again, that's going to be 4 minus 2, which is 2. Times the sum of the bases, so the sum of the two function values. So that's going to be the sum of 3.0 and 4.2. So that's how we would set up the area for the first trapezoid. Okay, for the second trapezoid, again, it's going to be 1/2 times the height. Now the height is 6 minus 4, so once again, that's going to be a 2. Times the sum of the two bases. So that's going to be the sum of 4.2 and 7. For the third trapezoid, now we're going from 6 to 9, so that's 1/2 times 3 times the sum of those two bases, so that's going to be 7 plus 5.4. And finally, for the last trapezoid, we're going from 9 to 12, so again, that's a height of 3, and then this time the two bases are 5.4 plus 2.4. And when you carefully type all of that into your calculator, you should end up with 48.7. All right, so those are the 4 different approximation methods. On the AP exam, you might be asked to use any one of these in a particular problem where they have given you a table of values for some function. Okay, now, just to wrap up this lesson, in the very beginning I said calculus focuses a lot of time and energy into this idea of finding the area under the curve. And I said that I would try to explain a little bit about why that's the case. So very briefly, if let's say that our function is actually not in terms of x and y, maybe it's in terms of t and some function f of t. And maybe t is measured in minutes, and maybe f of t is measured in gallons per minute. So maybe it's talking about, I don't know, maybe it's the rate at which water is leaking into, filling up an aquarium. Well, if the function looks something like that, so again, in this case, the function represents the rate at any given time. So at time maybe 1, the water is filling that aquarium at that particular rate in gallons per minute. Well, if I find the area under the curve, remember that that was the result of adding several rectangles where I was doing base times the height. But in terms of dimensional analysis, if I'm multiplying base times height, then that means I'm multiplying minutes times gallons per minute. And that means that the minutes actually cancel out, and we're just left with gallons. And so if I have a function that represents a rate of change, then finding the area under the curve on some interval from A to B actually tells me the total quantity that occurred over that time interval. So again, if F was representing the rate at which water was flowing into an aquarium to fill it, then the area under the curve from A to B is actually going to give us the total gallons of water that went into the aquarium during that time interval. And so that's one of the reasons why we study area under the curve, because the mechanics that are going to be involved to find that area actually allows us to find what's called an accumulation of a rate of change. How many quantities accumulated over that time period if our function represents a rate of change of that quantity. So that's where we're heading with all of this. Okay? All right, good luck.